The camera died again, but it's okay. So we're saying that we have a negative negative momentum because we have a negative velocity that will turn into positive. So we cross off A and B because those both start negative but do not go up to positive. So that leaves us between C and D. But we also said that the final velocity or the final momentum of each one will be less than their original momentum. So this one doesn't make sense because you're changing signs, but it's keeping the same magnitude. So C is decreasing in magnitude and flipping directions, which is what we said would happen. Number 13, so a student stands at one end of the raft floating in the pool, and there are equally spaced marks. The student begins to walk to the opposite end of the raft, and we know that if the student walks forward and there's no friction, there's no drag force between the water and the raft, then the raft will move backwards because the total momentum of the system, the two of them together, was 0 beforehand, before he started working. And if momentum is conserved, which it should be, then the total momentum would have to be 0 afterwards. So that means that the total momentum, the momentum of the person plus the momentum of the raft, would have to add up to 0. So that just means that they're equal to each other, just in opposite directions. So this guy, however much this one goes forward, is how much this one goes backwards. And because they are equal momentums, and it said that they have the same mass, they're going to go forward and backwards at equal velocities. Just one this way and one raft the other way. Now we started at the second little mark right here. So we're just picking the one that has the person going forward and the raft going backward. And actually C is the only one. So this one, the person goes one forward and the raft goes one backwards. Here, the raft stays in place, but the person goes forward. Here, they both go forward. Here, the person stays in place, but the raft goes backwards. The only one that made sense was C. Number 14, so we've got a circuit that has two resistors, a 200 and then a 400, and then a internal resistance, just part of the battery, of 10 ohms. And we want to know the relationship between these three currents. So I is like the current coming out of the battery. I1 is the current that is coming out of resistor 1, and I2 is the current coming out of resistor 2. But this one's actually really easy because you don't lose current through a resistor. You might drop voltage, drop potential difference of a resistor, but you don't lose current through a resistor. The current is the same in the same path, and there's only one path for it to follow. So this is actually, they're all equal to each other. You can think about it as this is a series circuit, so they all should have the exact same current going through it. Okay, yeah. Number 15, when two charged massive objects are placed a distance r apart, the gravitational force between them has a magnitude F. When the distance between the objects is increased to 2r, the magnitude of the gravitational force becomes F over 4. Well, we know that because gravitational force is gm1m2 over r squared. But if you have 2r squared, that is 1/4 the original force of gmm over r squared. Did the electrostatic force between the objects also decrease to 1/4 its original magnitude? So let's think. So K, Q1, Q2 over R squared. If I put a 2 right here, then yes, this would be 1/4 the electric force. This is 1/4 the gravitational force. So you should say yes because both forces have the same over R squared dependence. So if I double R, that would be 1 over 2, double R, that'd be 1 over 2 squared, which would be 1/4 the force. Gravitational force does not always equal the electrostatic force at any given distance. That is not true. In fact, the electrostatic force is generally a much larger force than the gravitational force. You can look at your constants to remember that. The gravitational constant is much smaller. Yes, that is absolutely true, but we're not talking about the forces being we're talking about how much the same. It's how much the forces change being the same. 1/4 the force time and 1/4 the force. They're changing by the same ratio. No, because the gravitational force is only attractive and electrostatic can be repulsive. This is a true statement. Gravitational is attractive and electrostatic is repulsive if they're the same. But that doesn't affect the magnitude. That just affects the direction of the force. 16, a clay ball and a rubber ball are the same of the same mass are moving towards a glider that is at rest. The balls each have the same speed. moving to the right, moving to the left. The balls strike this glider at the same time. The clay ball sticks to the glider, and the rubber ball bounces off of it, which of the following integrates the motion of the glider after the collision. So one way to think about this is just like total momentum here. If they're equal masses and they're both going the velocity v, they have equal momentum, so this has a total momentum of 0. So then when the rubber ball bounces off, I'm going to have to go down here. When the rubber ball bounces off, it has a momentum to the left. And then the glider, and of course the clay ball is going to stick to the glider. Well, these two are stuck together. They're not going to go to the left because they have to still have a total momentum of 0. So the two of them stuck together need to still go to the right. So we can cross off C and D because we know just for momentum to be conserved, then these two have to go to the right. And now it's just thinking through, like, okay, what is the correct explanation? B says the glider moves to the right because the collision with the rubber ball is elastic and conserves energy. That might be true. That might make it conserve energy, but I don't know why this ball conserving energy would make this one go to the right. So I'm going to cross that off, leaving A. Let's think through. The glider moves to the right because the magnitude of the change in momentum of the rubber ball is greater than the magnitude of the change in momentum of the clay ball. That is definitely true because this rubber ball comes in with the same momentum, but it stops, turns around, and goes the other way. Whereas this one, because this is like has such a greater impulse, it's pushing or creates a force or impulse on the glider so much the other way. Which means that the clay ball, when it sticks to, is going to just take that and go the other way. 17, a lion running at a constant speed towards a gazelle that is standing still, as shown in the top figure. So at first, this one is still, and this one is going to the left at a constant speed. Then the gazelle notices the lion and accelerates directly towards him, hoping to pass the lion and force him to reverse direction. So then this gazelle is accelerating, so she is increasing velocity. The lion has to stop and turn around and go the other way. So the lion is now going this way, and he is accelerating. And then they both reach constant and then constant after a couple seconds, I guess. So let's start with the gazelle because that's an easy one because at first the gazelle is still for a couple seconds before they accelerate and then reach a constant speed. So we can cross off B and C because they show the gazelle accelerating immediately, whereas it said she was still for a couple seconds and then accelerated and then got to its constant speed. So now we're between A and D. So we have to look at the lion. So the lion at first was moving to the left at a constant speed, had to turn, accelerate, and then is now moving to the right at a constant speed. This shows going one direction and then just getting faster in that same direction, where actually it was going one way and then turned around and went the other way. So A is the correct one for both the lion and the gazelle. A spacecraft of mass 4,000 is traveling in a straight line in the positive direction. Engines can be fired so that the force exerted on the spacecraft is in the positive or negative direction. So we see we have a positive force, but we also have a negative force later on. The graph shows the data for the force during one interval. Which of the following is the best estimate in the net change of speed of the spacecraft from 0 to 4 seconds? So we're talking about the change in speed. So change in speed. And we've been given force in time. Now, if you look at force times time, that's going to give me change in momentum. And if you're like, okay, well, what does that have to do with change in velocity? Well, change in momentum is just mass times change in velocity, and I have the mass. So what I want to do is I'm going to use area under the FT graph. So this is just area under the graph. And that's going to get me my change in momentum, which I can plug in here. So this is of course not a straight graph, right? In that straight line. So let's work on, do a good estimate. Maybe starting 1,000, and one thing that people might make a mistake is they're like, oh, it goes to 3. This is not a straight line, but that's okay. See how this is a good estimate, because I have some points that are slightly below it, but I also have some points that are slightly above it, so that would kind of reason out. If I were to go from here to here, I'd be taking in a lot of area that that doesn't really like show force in time because that's not a force applied in here. So this is a much better estimate. So this one is a triangle. That would be base times height divided by 2. So that would give me like 1,500. Oh, geez, 2, not 3. So that would give me just 1,000. So this would be a positive 1,000. And then you wouldn't really do an area in here because this is just kind of force is 0. There wouldn't be a change in momentum in here. And then here you can either do like a triangle. I did like a kind of a rectangle in here because it looked pretty flat, just this one outlier right here. But again, just an estimate, just try to do the best you can. So then this would be base of 1 times height of negative 500. So this one has a change of negative 500. So if you're changing positive 1,000 and negative 500, overall your change in momentum is positive 500. Mass of 4,000, change in velocity, divide the mass over. I got like 0.125. I think with these numbers I got 0.125, so then the best answer choice would be the positive 0.1. Because I'm getting a positive number out because I might be losing momentum at the end, but I gained more than I lost, so overall I gained. Okay. A rocket is continuously firing its engines. It accelerates away from Earth. For the first kilometer of its ascent, the mass of the fuel ejected is small compared to the mass of the rocket. For this distance, which of the following indicates changes, if any, the kinetic energy of the rocket, the gravitational potential energy of the Earth rocket system, and the mechanical energy of the Earth rocket system, what if they're increasing, decreasing, staying the same, etc. So let's start with the rocket's kinetic energy because that's pretty easy. If it is accelerating away, then it is getting faster, so its kinetic energy should be increasing. So I'm going to cross off D. The system gravitational potential energy. So we usually do gravitational potential energy. The UG is just MGH. But MGH only works for like certain heights above the Earth. As soon as you get too far away, then it gets complicated. That's not just potential energy where your height is the distance above the Earth. So you have to actually look at your equation sheet. We haven't used this one before, but it's right here, potential energy. So that's mg like delta y or mgh. Or it can be between two masses with the distance between them. So g/m over r. And you'll notice that there's a negative sign right here, which is weird because energy doesn't really have a sign, but potential energy between two planets does have a sign. It's negative. So the gravitational potential energy, well, your masses of the rocket, it says it's very small, like losing very little mass, so that's basically staying the same. Between the rocket and the Earth's mass is definitely staying the same. This r is increasing. So I have this one is negative g/m over r squared, just r, not r squared. So if r is increasing, if I'm dividing by a bigger number, that makes it smaller. But it is a negative, so when you get smaller with a negative number, getting smaller with a negative number is actually getting closer to like going on the positive. This is a hard way. Basically, if you have a number line, let's see if I can do this. This is 0, this is like -1, -2, -3, -4, 1, 2, 3, 4, 5. This way are bigger. Hopefully everyone agrees with that. So I have a -1 that becomes -5. Technically, that is a smaller magnitude, but that is a bigger number. So my gravitational potential energy is actually increasing. As I get farther away, this number gets smaller, but that's a smaller negative sign, which is technically a bigger value. So this should be increasing and increasing. So we can cross off D. And then your system mechanical energy, well, let's just think about if our kinetic energy is increasing and our gravitational potential energy of like the rocket and Earth is increasing, then the rocket and Earth system, if these two are both doing the same thing, then this one has to be increasing as well. The reason B doesn't make sense for the constant is you can't have kinetic energy increasing and potential energy increasing and stay constant. Now, if you're like, what? Energy is supposed to be conserved. So energy for sure is conserved here. Part of this is like basically you're ignoring the fuel that's being ejected out. So it said it's ejecting fuel, but it only said the rocket, not the Earth rocket fuel system. So here the engine's like ejecting fuel is like putting work into the system. So it's gaining its energy because its engines are on. Block 1 is attached to a spring, oscillates on a horizontal frictionless surface. When block 1 is at the point of maximum displacement, block 2 is placed on top of it from directly above without interrupting the oscillation, and the two blocks stick together. How does the maximum kinetic energy and the period of oscillation with both blocks compared to those of one alone? So let's talk period because that's the easy one. You have an equation, 2 pi squared of mass over k. Obviously, when you place a second mass on block on top, you have increased the mass. If you have more mass, then you're going to have a bigger or more period, so you're going to have greater periods. So we can cross off A and C. Now, what happens to the maximum kinetic energy is a little bit trickier. What a lot of people want to do is they're like, okay, kinetic energy is 1/2 mv squared. Let's get that up. And if your mass increases, then that would increase the kinetic energy if your maximum velocity stayed the same. But let's think about if this is like the whatever spring, if this is equilibrium, and it got stretched out to its maximum point right here, and I added a second mass on top, it's still holding the same spring energy as before, because spring energy is just kx, so the spring holds the same energy, but when that spring energy is transferred into kinetic energy through here, now it's dividing the same amount of energy over both masses, so it'd actually be going smaller. So let's think about it as this potential, spring potential energy is where the kinetic energy comes from. So if I drop a second mass right here, my potential energy is just 1/2 kx squared. I haven't changed the spring constant. I haven't changed my displacement k. So then that means that I haven't changed my spring energy. So the maximum spring energy at this point is where this maximum kinetic energy comes from. So the kinetic energy is staying the same. A child slides from rest down slides A and B. The slides are the same height and the coefficient of friction is the same. Which of the following compares the change in kinetic energy to the change in potential energy of the child Earth system for the two slides? So let's start with change in potential energy, because change in potential energy is just mg delta y. Here it says that the slides are the exact same height, so this one is losing the exact same amount of potential energy as this one is losing. So the potential energy change for A and B would be the same. So now for A and B, which means our answer choices are now A and C, because we can cross these two off, so they were different. Your kinetic energy, so it's tempting to be like, well, if they change by the same potential energy, and then they change by the same kinetic, because that kinetic energy comes from potential. But it had in here that we're talking about coefficient of friction between the slides. If there is a coefficient of friction, that means that there's work being done. So there's definitely work being done, there's energy lost. And the kinetic energy is not, so in this case, the amount of kinetic energy that the child has at the end is not the same as the potential they started with, because they've lost along the slide some of that energy because friction is doing work on the system. Okay, so why would they have different work done to them? Well, work is the force times displacement. So if you have roughly the same friction force, but you do it over a longer distance, see how this one loses more energy? If this one loses more energy than this one does, then the kinetic energy at the bottom is not going to be the same. So we can cross off A, and that is C. And if you're like, wait, but this one says that A has a greater change, that's true, because here, let's say they both start with like 10 joules and 10 joules, right? If this one loses, I don't know, 4 joules, they have 6. This one loses only 1 joule, they have 9. So the change in kinetic energy from 0 to 9, and then from 0 to 6, this one changes because it gets most of its kinetic energy, most of its potential into the kinetic, whereas here it loses more of it, so less of it changes into kinetic, if that makes sense. First of all, unknown mass oscillating horizontally, ideal spring. They measure the period of oscillation with a stopwatch. They want to determine the spring constant of the spring using the period. What other pieces of equipment would provide another measured quantity that is sufficient information to complete the determination of the spring constant? So we're looking for what is K, and we know T. So look at your T is 2 pi square root of m over K equation. If we know this, we want K and we know T, well, we know 2 pi as well. That does not look like want. That's okay. That means we need the mass. So meter stick doesn't help me get the mass. Motion sensor, that would help me get like the velocity of the position, but not the mass. A balance, yes, that would help me get the mass. A photogates measure like speed or velocity, so that again would not help me. Using a number of measurements, the student determines the following. We've got spring constant, that's K. We've got the mass of the object, M. We've got the amplitude, you could call this A, or you could call this like X max. This is maximum displacement, X displacement. And then maximum speed, I'm going to call this V maximum. We want the total energy of the Earth's spring system. So we have two types of energy. We've got the spring energy, and we also have the kinetic energy. So I'm going to find the maximum spring energy, so that would just be 1/2 kx squared when I use the max x, and then maximum kinetic energy would be 1/2 mv squared where I use the maximum velocity. So if I do 1/2 k85 times x 0.3 squared, and I can do 1/2 mass of 0.5 times velocity 3.9 squared. For the spring potential, I think you get like 3.8 something. Let's double check. 3.8025. And then for this one, you get 3.825. We're looking for total energy of the system. And one mistake I've seen people do is they add these two because they're like, oh, total, that's both of my energies. But you never have these two energies at the same time or at the same position, right? It goes from, this is my equilibrium. It goes from stretch to all kinetic to compressed, which is all potential energy. So at this point where I would have 3.8025 joules of potential energy, I would actually have 0 kinetic energy. And at this point where I would have this much kinetic energy, that's the maximum at the equilibrium where I have no potential energy. So just one of these is the total energy right now because I only ever have all potential or all kinetic. There are times where I have some of both, but not these values of both, right? This is 3.8 and 0, and this is 3.8 and 0. So the total energy is 3.8. 24. While the object is continuously oscillating, the student determines the maximum speed during 2 oscillations. The first maximum speed is 3.5, and then the second maximum speed is 2.7. Which of the following would account for the decrease in the object's maximum kinetic energy? So why would their maximum kinetic energy decrease? Maximum kinetic energy is saying, like, I'm not sharing my energy with some kinetic, some potential. This is all KE right here. And the amount that is all KE is decreasing. That means I'm losing energy overall. So it says energy is transferred from the object to the spring, which increased the maximum potential energy. That doesn't make sense because at the maximum kinetic energy, it's still all kinetic, no potential. So if this one all of a sudden has more potential energy when it has no kinetic, then that doesn't make sense because the total would be changing from one point to another. Energy is transferred from the spring to the object, which decreased the maximum potential. Well, if it was like oscillating, it's very possible it's transferring back and forth, and your maximum still is staying the same, so that doesn't really help. As the energy was transferred back and forth, a greater average share of the energy became potential energy. Well, at this point, I have 0 potential energy, so these are not addressing the problem of my total kinetic has decreased. And then the last one, it loses energy to the surroundings. This is most likely. This would be like friction, etc. work, like friction is doing work, so that the total energy is slightly decreasing, which is why my total kinetic and my total or maximum potential would be decreasing, because just all of the total energy is decreasing. All right, we've got a crate on a horizontal frictionless surface. A force of magnitude F is exerted at an angle theta, causing it to slide to the right. The surface exerts a normal force Fn on the crate. As the crate slides a distance d, it gains amount of kinetic energy delta k. While F is kept constant, now the angle is doubled, but still less than 90 degrees, assuming it remains in contact with the surface. So I'm going to draw free body diagram real quick. I have right now, I've got like Fy and Fx, and because the angle is so small, I drew Fx more than Fy, and then of course got the normal force and the force of gravity. This was our Fn right now. Now it says I'm doubling the angle. So if I double the angle, now it's something like this. Now it looks like it might be more up than over, so I'm going to redraw. Now my Fy is definitely bigger, and my Fx is definitely smaller than before. Fg, of course, is staying the same. So if Fg stays the same, but I'm now pushing up more with the y force, that means my normal doesn't have to be as big anymore, because these still add up to the same gravity. So my normal force should be less than before. So your new normal force is less than Fm. And then how does the gain in kinetic energy now compare to the gain before? Well, I think about it in terms of acceleration. So here, this one is going to have less acceleration. So then it's not speeding up as much, it's not gaining as much kinetic energy. So it has less change in kinetic energy. You also can think about, okay, the change in kinetic energy is coming from work done. Work is force times distance, specifically is like the Fx. That is less, right, that is causing the work that's, Fx times the distance. It's still sliding a distance d, but now in this work, or this change in kinetic energy came from the Fxd. Now I have less Fx, but over the same distance, so I'm going to have less change in kinetic energy. That's also another reason why. God, we're only halfway through. Number 7, a block on a level surface is attached at one end of a spring as shown in the figure above. The other end is attached to the wall. There is friction between the block and the surface. A person displaces the block from its equilibrium position and releases it, which the following shows mechanical energy as a function of time that includes only the block, and the system that includes the block and the spring. So if we're thinking about this right here, let's say it's compressed. That means that all of the energy is potential energy in the spring. And then it's released, and that is going to go into kinetic energy, and then it starts to stretch out from equilibrium, and then it goes into stored energy in the spring, and then it gets like starts turning around and gets faster, so now the block is gaining energy. So the energy that just includes the block is going to be oscillating back and forth and back and forth, because it goes between the spring and the block, the spring and the block, the spring and the block. So I can cross off C, because that doesn't make sense, because I do know that the block will be gaining and losing energy, because it's going from spring potential to block kinetic, from spring potential to block kinetic over and over again. It says, and we have to be very careful, that there is friction between the block and the surface, which means that there's going to be work done, which means that you're going to have a change in energy. Overall, this is going to be losing energy. So we can cross off B, because this says that their energy is going to be constant when we know we're going to be losing some of that energy. Now we're between A and D. So we have the same graph for the just energy of the block. The second graph is energy of the block and the spring. The energy of the block and the spring shouldn't be oscillating, because if I am going from the potential to the kinetic, if I'm talking about both of them together, that's just the sum of the energies. The sum of the energies, so both kinetic and potential, isn't oscillating. In fact, ideally it would be the exact same, but because I'm losing friction, I'm losing because of friction, it's decreasing, so it would be D. Transverse waves traveling along a string. The graph shows position as a function of time for just a specific point on the string. So this isn't like a picture of the wave. It's saying, okay, one point on the string goes up and then down and up and down this much in this amount of time. If the frequency is doubled, was the new average speed of the point. So average speed of the point is just going to be distance over time. We're not talking about the speed of the wave. That is different. This is the speed of a specific point, so some distance and some time. Right now, we can't just say like, oh, this many meters in this much time, because the frequency is going to be doubled. So this isn't the correct time. If I double the frequency, instead of having just one wave here, now I would have two. So it looks something like this. Instead of my period right now for one wave is just 0.5 seconds. Now my new period is going to be half that, because now I'm fitting two waves in that time. So my new period is going to be 0.25 seconds. My amplitude isn't going to change if I change the frequency, so I'm still going up 0.6, down another 0.6, so that's 1.2, down another 0.6, and then up again, so that's another 1.2, so I'm going 2.4 meters in just one oscillation. And the time for one oscillation is now 0.25 seconds instead of the 0.5 seconds. So this distance over this time gives me this speed. If you get 4.8, that's the speed of the wave that as shown. If I double the frequency, you're going twice as fast because you're fitting in twice as many oscillations each side, or each period. Opposite sides of the room, don't hear them, so louder, and now he hears it. What is different? Well, louder, when we're talking about volume, that is the amplitude of the sound wave, because volume has to do with the amplitude. Pitch is like your frequency. So how is it different? We just want the one that describes greater amplitude. The second wave travels quickly. No, that's not true. The second wave reflects more of the walls. I don't know why that would be true. The air molecules disturbed by the second wave undergo a greater displacement from equilibrium. The definition of amplitude is the displacement from equilibrium, the maximum displacement from equilibrium. So this one is just describing a greater amplitude. Molecules disturbed by the second wave are on average more closely spaced. That would be a smaller wavelength. Smaller wavelength would be a higher frequency. That would sound like a higher pitch. Two strings differing only in length are attached to the same oscillator as shown above. They are under the same tension, and it says the strings are differing only in length. So they're like basically identical strings, just the length is different with the same tension. That means same velocity. So we can cross off A, that's saying they would be at slightly different speeds, because it says they're basically the same string and the same tension. The length doesn't affect the velocity. The oscillator creates a transverse wave, is adjusted to the lowest frequency, and creates a standing wave. So lowest frequency would be something like this, first harmonic standing wave. Which of the following explains why there will not be a standing wave on the longer string? Well, let's think about it. They're attached to the same oscillator, so this would be the same frequency. If you have the same frequency with the same velocity, then that means you have to have the same wavelength. So this would be, have to have a wavelength like this, and then of course it would continue on. So this is not going to create a standing wave because you have to have like the perfect lengths that are like basically multiples of this length right here, of the half wavelength. So your answer is that the wavelength associated with the given frequency does not match the boundary conditions. Boundary condition meaning like these two have to be fixed in. So here I have fixed, and then like the wave half wavelength would end right here and start. That's not going to match up with what my two fixed ends are going to look like. A lot of people, if you miss this on the test, you mainly put B, saying that frequency on one length will not result in a frequency working on another length, but that's not true. Some lengths would work. In fact, if this one was like, I don't know, 3 meters, if I had 6 meters, that would work because it would just be twice the wavelength, and I would get 2 of these right here. Or sorry, not twice the wavelength, twice the length, so I would get 2 of the half wavelengths because it's still the same wavelength. So it's not that no string would, no other length would work. Some lengths would work, but it's very, very particular. It has to match up with the original boundary conditions. Net force as a function of position, and we have that it started from rest and then gained a speed of 3. So this is like my V final, and my V naught was 0. And we've got distance and of course like this changing force. So we are looking for mass. Well, we have velocity, so I'm writing mass and velocity to force and position. So let's think, I know the area under a force position graph represents something. So this would be force times change in position, right? So F delta x, I don't see F delta x on here, but hopefully you're like, oh, change in position, that's just the distance, right? So F distance is the work, which is also change in energy. So that's going to help me because this looks like it could be change in kinetic energy. So let's first find the work. So this is area under the curve. This is a triangle. Don't just do 3 times this because it's a triangle. It's base times height over 2. So 3 times 0.09 over 2. That gives me a work of, let's see. Work is then 0.135. Well, work is changing kinetic energy in this case because it's talking about starting from rest and then accelerating, so that's where that work is going into, is kinetic energy, because work is also change. So work is going to be my change in kinetic energy, which is K final minus Ke initial. Well, it started from rest, so that's just 0, so work is just my final kinetic energy, because it started from rest. So 0.135 equals 1/2 mass V final squared. This is 9, half of 9 is 4.5. Divide over, and you should be getting a mass of 0.03 kilograms. 2 identical carts free to move along a straight frictionless track. At T1, cart 1 is moving at 2 meters per second, and it collides and sticks with cart Y, which was initially at rest. So I've got this cart coming in with a velocity of 2, and then it's hitting this cart, and then they stick together. So now they're going to go off. They should be going off at a smaller velocity than before for sure. So we can cross off A, and we can cross off D. It's not going to go to 0. There's definitely still moving. It's just the momentum of this guy is now split over both of them. So I know it's getting slower, but this one looks like I need to know exactly how much slower. So let's go back. It tells me identical carts. That means these are equal masses. So if this is a mass, or this has a momentum of 2m, and then it picks up a second mass, now it's splitting its momentum over twice as much mass, so it'll have half the velocity. It's giving half of it away right here, so they can now go at the same velocity. So I want exactly half the velocity, just one, so that was C. And I only am able to do that because it tells me they're identical, they're equal masses. If this was a greater mass, then it would have slowed down a lot. It would have jumped like closer to 0 or like below the 1. If this was a smaller mass, then this one would have worked because it's not halving, right? It's only giving a little bit away. That's only slowing me down a little, but it was the exact mass, so it exactly halves. A spaceship and its shuttle are traveling to the right in a straight line with a speed of v, so that's the first one. And then what happens? Okay, so they have a mass m and a mass 6m. The pod is launched, and afterwards the pod is moving to speed with vp, and that makes this one, oh sorry, this is going this way? Oh, that's so weird. Anyway, it's still going this way, but I guess less than this one, which is now going faster. And we want to know what is true about the speed of the center of the mass after it is launched. So AP Test loves these center of mass questions. The velocity of center of mass is super easy. So your V of the center of mass, the velocity of center of mass, is going to be the same unless there's an external force. Here, there definitely was some force between these that made this one go faster and this one go like slower in this direction, but it was between the two of them. It doesn't say anything about another force coming in on the system, so there was no external force. So the center of mass is the same as it was before. Well, before the two of them were just moving to the right at a velocity of v, so of course the center of mass was just v, so it's still just v. Oh, d equal, not just said it was the same, not less than. So it is just equal to the original velocity v. This one might be going faster, this one might be going slower, and it might be going significantly faster and significantly slower, but the center of mass velocity would average out to the same as original, because no external force. We've got a circular platform, a mass 5m, and a person with mass m, our child, and is rotating counterclockwise. Which of the following would describe an action by the child that would result in an increase in the total angular momentum of the system? Angular momentum of a system is conserved unless, so the total, right, keyword here, total, this is conserved unless there is an external torque. So that is my answer, D. None of the actions are going to, will change the total angular momentum, because moving towards the center or the way or along the circle, those are all forces the child is exerting on the platform. That's between the two objects, right? That is not an external and outside torque acting on it. So none of those would work. The child moving towards the center, you might be like, wait, but that's going to make it go faster. And that's totally true, because you would be decreasing the rotational inertia, but that just makes the omega increase as compensation to keep L the same. And then same with moving away. That would increase the rotational inertia, it would make it go slower, but that keeps the exact same rotational inertia. Moving along in a circle opposite the direction of the rotation, that would make her, let me think if it's opposite direction. That would make her go slower and make this thing go faster, but overall it would still be the same total momentum. You need an external torque to change that. A train is traveling east with a constant speed Vt, so I'm going to say like the train itself is going at a constant speed Vt. Two identical spheres are rolling on the floor in the frame of reference of the train. The spheres are moving directly towards each other at one instant with the speed, same speed Vp. So this is the speed of them towards each other. And I want to know what's the velocity of the center of mass of the springs in the frame of reference of the train and in the frame of reference of the person standing at rest alongside the train. So here we have to be careful because we have two different frames of reference. So if we're going to just say, okay, from the frame of reference of the train, that would be like if you are standing inside of this moving train and just watching these two balls roll towards each other, then and their equal masses coming at equal velocities, their center of mass is just at rest, right? Their center of mass is just here. If one was going faster than the other, so let's say I had two masses, but this one was going way faster than this one, then my center of mass would be going to the right. Or if I had, they're still the same velocity, but this is a much bigger mass coming towards each other, then this would be a center of mass velocity to the right. But that's not what's happening. They're the same masses, they're equal speeds, so this center of mass velocity is actually just at rest, because these two, however much this one moves the mass over to the right, this one moves the mass over to its mass over to the left, so that just cancels out. So the center of mass for the train reference frame is 0. Now, the tricky part here is the center of mass from the reference frame of somebody watching on the train, watching outside of the train. So if I am this person right here, well, the train is moving with a velocity. So these guys, their center of mass might be at rest relative to somebody sitting in the train. But if you're outside the train, well, this is a rest to you, but you guys are both moving. So the velocity of the center of mass would just be the velocity of the train. So B. A satellite is spinning, that is a spinning cylinder, has an initial rotational inertia I naught and an angular velocity V naught, not V naught, omega naught. Solar panels unfold from the satellite and are extended outward. So I'm keeping the exact same mass, but I'm now distributing it out more. So that means you're going to increase the rotational inertia because your mass is distributed farther from the center of rotation now. And then if L equals I omega, well, if I increases, that means this one decreases because this one is still conserved. So the momentum has to stay the same because there's no external torque. So I have more rotational inertia. So that means that like A is a factor that makes it increase, and I have less, angular speed. So B is something that will make this decrease. So I know I can cross off the things that are 1, that's saying they stay the same, and that's not true. This one's increasing, this one's decreasing. 1 would say that they're just equal. And they're not doing the same thing, right? It's not increasing and increasing, so I'm going to circle B. A greater than 1, that makes sense. When you multiply by a number greater than 1, this is going to increase. be less than 1, so like 1/2, 1/3, 2/3, etc. When you multiply it by a number less than 1, that's going to make this decrease. 37. When the circuit shown is set up, the potential difference across the battery is 3. By how much will the magnitude of the potential difference across R2 change when R3 is removed and its branch is left open? So let's actually calculate. Let's find what the potential difference is right now, and then we'll find what it is after. So I'm going to start with finding R total. R total here, I can't just add these all together because these two are in parallel with each other, but then these two combined are in series with this one. So let's combine the 1/100 plus 1/100. Don't forget to do 1 over that. That would give me just these two in parallel with each other, and that's going to give me 50. So these two, that would give me 50. And then if I have 100 and a 50, like this, terrible circuit, but that gives me a total resistance of 150 ohms. Now, if this is my total potential difference, or my total voltage of the battery with the total resistance of 150, I equals voltage over resistance. That gives me a total current coming out of the battery of 0.02 amps. That means this resistor is getting the 0.02 amps, so 0.02 amps with a resistance of 100 gives me a voltage drop of 2. And then because I have a total voltage drop of 3 and this drops 2, then that means this one drops 1. And this was in parallel, so it would also drop 1. So 1 volt and 1 volt. Now I'm going to take out resistor 3. So now it's just a 100 and a 100 hooked up to the 3 ohms. It's supposed to be a battery, or 3 volts, sorry. So then now my total resistance is 200, voltage of 3 volts, 200. That would give me a current of 0.015. And then so this guy is now getting the total current. So 100 ohms times this many amps would give me 1.5 volts. So first it was 1 volt, and now it is 1.5 volts. So that means that if I'm going from 1 volt to 1.5 volts, you are increasing by 0.5. So that is C. 2 wave pulses, what is the resultant when they align? So here I have up and down. There's going to be some destructive. So when I have this, basically this is like a subtraction. Oh, this looks so weird. Anyway, so right here, this would still have its full momentum or amplitude because there's 0 here. This would have its full because there's 0 here. But then these start canceling out, so this is going to start to decrease. They have the same height, so in the center they completely destroy. And then here it's like decreasing until they completely destroy too, so it's C. A person holds a 4 kilogram block at position A as shown, and they're above an uncompressed vertical spring. So if it's uncompressed, that means the spring is not holding any potential energy in it right now. And we have the spring constant K, so we've got mass in K. The person gently lowers the block from rest at position A to rest at position B. Which of the following describes the change in energy of the block spring system as a result of the block being lowered? So I looked at the change in energy. So let's think about, I have 2 energies that are changing here. I have potential energy, gravitational potential energy, and I also have spring potential energy. So let's start with the gravitational potential energy. So the change in gravitational potential energy is just mg delta y. So this is, keep going here. We'll do spring over here. Mass is 4, g we'll just use 10. And how much the y changed? Well, it went from 30 to 20. So that means the change in y was 10 centimeters. But we don't use centimeters. That's going to be times 10 to the negative 2. So that's going to be 0.1 centimeter. So that means that my gravitational potential energy changed by 4 joules. And if I am decreasing in height, that means I'm losing 4 joules. So the potential energy lost, gravitational potential energy lost 4 joules. Now let's talk about the spring energy. So the spring energy, at first, there was none, right? So my spring energy is just the 1/2 kx squared that I now have. I have k, it's 500. the X, and it's careful here because 20 is not your X. X is the displacement. If it was normally at 30 centimeter at equilibrium, if it's squished down to 20 centimeters, then your X, your displacement, is 10 centimeters, or the 0.1 squared. So then that gives me a change in spring energy of 2.5. And here I am gaining energy because at first I had none and now I have potential energy, spring potential energy. So I'm losing 4 joules of gravitational, but I gained 2.5. So then overall I lost 1.5 because plus 2.5 but minus 4 gives me minus 1.5 overall. The other way you could have thought about this is, okay, how much energy do we have at each one? So if you just start with, okay, right here, my potential energy is mgh. That's 4 times 10 times a height of 0.3 meters. So that would be 12 joules right now. So this one has gravitational potential energy of 12 joules. Here, my gravitational potential energy is mg, but now my h is only 0.2, so that's only 8 joules of potential energy. But now I also have spring energy, 1/2 kx squared, that's 1/2 k is 500. The x, the displacement, was 0.1 squared, and that's going to give me 2.5. So then here, I started with 12 joules of gravitational. Here I have 8 joules of gravitational, but 2.5 of spring energy, so I have just a total energy of 10.5 joules at this point. So I started with 12, now I have a combined of 10.5, so that means I lost 1.5. That's the other way to think about it. I'm not going to go through these because I have a video of me going through it on the entrance quiz for Mondays. This one, I think it's D, C, and, no, sorry, A, C, and D. Let me just double check. Doing that from memory. Yep, A, C, and D. If you need explanations, go to that video. A researcher is analyzing data from high-energy particle collision. The result of the analysis gives this value, 8.8 times 10 to the negative 19th, give or take, or plus or minus 0.1, for the charge of one of the emitted particles, should the researcher accept the value. So let's look. Some charge we should never accept because charge has to come in increments or in multiples of the smallest charge, which is the charge of an electron, which is charge of an electron, that is the 1.6 times 10 to the negative 19. So let's look. This charge is 8.8 times 10 to the negative 19. So let's divide 1.6 e negative 19 and see how many elementary charges that would be. That's not showing up very well anyway. So that would give me 5.5. That would be 5.5 electrons, which doesn't really make sense, but let's look. We have a margin of error. So let's say if it was 5 electrons. 5 electrons would be a charge of just 8 e negative 19 coulombs. If it was 6 electrons, that would be 9.6 times 10 to the negative 19th coulombs. Well, we have 8.8, give or take 0.1, so from 8.7 to 8.9, so definitely not within this range. So no, they should not take this information because 5.5 or however close it was is not going to be close enough to be an integer or a whole number multiple of the elementary charge, or the charge of an electron, 1.6 times 10 to the negative 19. Current through the 3 ohm resistor in the circuit above is most nearly, so careful here. It's tempting to be like, oh sweet, this is in parallel, just divide voltage by resistance. But these are not in parallel with each other because this voltage from here to here is the same, but from this side of the battery to the other side of the resistor, you're dropping potential difference right here. Some of that voltage is getting used up, so this is not 12 volts across here. This is a combination circuit, so I'm going to find our total first. So I've got the 1/3, 1/6, 1 over that, combining those two in parallel. Those two give me a 2 ohm resistance plus the 1 ohm right here, so this is an R total of 3 ohms. 12 volts, total resistance of 3 gives me a total current of 4 amps. So this has 4 amps coming out of the battery right here. which means that this guy with 4 amps and 1 ohm has a voltage drop of 4 volts. Now, if I have a total voltage drop, zoom in, glare is bad. If I have a total voltage drop of 12 volts and this one drops 8, that means that the rest of the loop has drops 4. The rest of the loop has 8 volts to drop. And then because these are in parallel, this one also has 8 volts to drop. I want to know what the current through the 3 ohm is. Well, current is just voltage over resistance. This guy has a voltage drop of 8 volts over resistance of 3 ohms, so that's going to divide and give me 2.7. A student wants to determine the speed of sound at an elevation of 1 mile. To do this, the student performs an experiment to determine the resonance frequency of a tube that is closed at one end. It's like ours. We did, like, the water made it closed and then it was open and we, like, heard the whatever. So hopefully you recognize this. Anyway, it doesn't matter, because the student takes measurements every day for a week and gets different results on different days. Which of the following experiments would help the student determine the reason for the different results? Because they're getting different, like, resonant frequencies, which shouldn't, like, the only reason you would get resonant frequencies or, like, different wavelengths is if your velocity is changing. So you're basically getting different velocities. And the speed of sound, oh, you can see, different velocities. The speed of sound in air should be pretty constant, right? Because you're not changing the medium, but temperature changes the medium, right? So maybe it was due to different temperatures on each of the days. So then repeating it on days that have the same temperature and another day that has, like, several different days at a different temperature but staying the same would test to that theory. These are my 2 answer ones. So a uniform plank is placed with a pivot at the center. The block is placed on the plank to the left of the pivot as shown. A student is asked to place a second block of greater mass on the plank so it would balance out and be horizontal. Which of the following quantities would need to be known in order to know where to place the block? So let's think about if this is my plank and the pivot point's in the center. I have this box. I need to, and I'm, like, placing, the bigger box is going to be slightly closer, but we need to know the exact distance in order to make it balanced. So here, balance don't mean balanced forces because this would cause rotation. You want balanced torques. Balanced torques. So basically, you want this torque to equal this torque. Well, torque is just F times R, so you want this F times R to equal this F times R. Well, the force we're talking about is just the force of gravity, right? So this is just mgr must equal mgr, but these are different masses, right? I'll call it M1 and M2, so you're going to get different radiuses, or they're not really radiuses, different distances to the pivot point or the axis of rotation. So in order to know what this one is, this is what you want to know. Well, G is just going to cancel out, so it doesn't matter. You need to know the masses of the block, right? You need the masses of the block, and you need this distance, R1, the distance from the pivot point to the block. So you want the mass of each block, and length of the plank doesn't matter. It just matters where I placed this one, which is the distance from the pivot to the left block, so B and D. The mass of the plank could matter if you, like, let's say you have the pivot point somewhere like here. Then your center of mass is now a torque acting on this pivot point. Then the mass of the plank would matter. But right now, because you put the pivot point at the center, that balances out it's like holding up the center of mass, so that doesn't matter. Block is held at rest against the wall. By a force of magnitude F exerted at an angle theta from the horizontal as shown. Let Fg be the gravitational force made by the Earth, Fn be the normal force exerted by the wall on the block, and Ff be the friction force exerted by the wall on the block. Which of the following about the magnitude of forces must be true? So I'm going to draw a free body diagram. Of course, we have this force right here. We're going to break that down into, like, obviously that is going up and over to the right. This is my angle right here. That makes this the opposite side. So this one would be like F sine of the angle. This would be the adjacent to the angle side. So this would be your F cosine. So if I'm to redraw this, I've got F cosine like this. and I've got F sine upwards. I, of course, have FG downwards. Now the normal force, it's super important to remember that the normal force is always perpendicular to the surface. So if this is my surface, the normal force is not pushing the block up. The normal force, the wall, is pushing this way against the block. So this right here is your normal force, like this. And then friction, you actually don't know which way friction would point, because if this is a big enough force to push it upwards, if it's like moving upwards, then friction would be pointing down. Oh wait, no, it says it's held at rest. Just kidding. Anyway, you don't know if it's held at rest because I have a big force and the friction is like too strong for the big force to overcome, or if the friction is helping this force hold it up. So either way, you don't know the force of the friction right now, but I'll just put plus friction somewhere in here. And it says that it's at rest, so that means these two are equal to each other. So that means my normal force is equal to F cosine of the angle, which is one of my answers, B.